Yeah, this attention here has the shape of 1 by batch size by 2 times source length. Okay, now we can start coding our training functions. So let's do the training function for one batch first. We're gonna take the input, target, our encoder and decoder models, and their respective optimizers. The criterion, the max length, actually the constant length, being the length of the branch source, and we're gonna partly use teacher forcing. So teacher forcing ratio, let's do a 0.5 as the default. So first, let's put our models into train mode because we do have dropouts. We need to put them into train mode. And zero grad the optimizers. And first, we want to check our input length. So at the zeroth dimension is batch size, and at the first dimension, it is the length of our source input. And we want to ensure this input length is equal to our max length and our target length. Also at dimension 1. And our batch size. Also, we want to ensure that our batch size of the target is equal to the batch size of our input. And we initialize our loss. So first of all, we send our sources into our encoder. So let's do encoder outputs. Encoder hidden. Actually, I will just call it hidden. And this cell being none for now. Now let's compute for our mask. The mask is simply where the input tensor is not a padding. So let's say input unequal to our padding token has an index of 0. So now we can start working on our decoder. The decoder takes one column at a time. It's actually a bunch of single words at a time. And at the start, it's a batch of start of sentence tokens with indices of 1. So let's do decoder input equals torch dot once with a size of batch by 1, and put it on our device. And of course, passed into int tensor. Yeah, and for the teacher forcing part, let's do tf is true if we want to import random here. If a random number between 0 and 1 is smaller than our teacher forcing ratio, else false. So what is teacher forcing and why do we use it? Let's say without teacher forcing, your model outputs a batch of words each turn, which are then thrown into the next turn as the inputs, no matter whether they are right or wrong. This is good and bad. The good thing is your model learns to predict long sentences recursively, but what's bad is that if your output from last turn is wrong, then all its following predictions will likely get wrong, which isn't that helpful to make good gradients to update its parameters. Then what we do to mitigate this is, no matter what it predicted for this turn, we send in target words of this turn as the inputs to the next turn. This way, we are actually focusing on if it's able to give correct results for one turn. But what's not that nice about teacher forcing is, since it's focused to one turn, the model won't learn how to overcome a wrong prediction with the information of all the previous turns and the encode outputs by itself. So this can cause it to stuck at a wrong prediction and not proceeding any further during the test stage. So here we kind of compromises with a random number to select whether or not we want to do teacher forcing. And in this way, both its short-term performance and the long-term performance can get trained. So if teacher forcing, so this is actually enumerating through the length of the target. And as I have just mentioned before, since we have sorted our target inputs, if we have encountered a full column of zeros, we know it's the end of all the sentences in our batch, so we can quit the loop. So let's do if torch.sum target at this current column is equal to 0, we break. So now we have decode output hidden and the attention at this place, but we don't need it in the training loop, so ignore that. And our decoder cell, in case we're using LSTMs, this will be decoder for our decoder input hidden encoder outputs cell and mask. Let's check our for function in the decoder. Yeah, decoder input hidden encode output cell and mask. So we're doing fine. In this encode output, no S, and our loss will be updated. It's between the decode output and and the target at the current column. And we will need to turn this into long. And I will want to divide this by our batch size just to make it more consistent. And remember, now we are using teacher forcing. So no matter our prediction for the next word is right or wrong, we are gonna use the ground truth. So the decoder input for our next round is the target at the current column. And we unsqueeze at the last dimension to make it have a desired shape. Else, if we are not using teacher forcing, so many of the aspects are the same. And we train the, and I mean we pass the arguments into the decoder for the function in the same way. But this time we will gonna need our prediction for the current word as the input to our next run. So we are gonna find the word that our model have predicted. So let's do value and the index equals there's a function called top k. So this just returns the value, the highest value in our tensor, as well as the index of the highest value. And the only thing we want is the index. So let's say decoder input will be our index. And we want to detach that in order to clean the unnecessary gradients from our last run. I mean, we don't need to take the gradients into the next run. And we compute our loss. Between the decoder output and the target at the current column, casted into long format, and divide by our batch size. Finally, after training this batch, we back propagate the loss, and we update the optimizers, and we return loss and our batch size. So before we are proceeding into the remaining parts of the code, I did try running it and found out several bugs, and I will fix them with you. So first here, we are just calling it cell because this output is cell, and we are also calling it cell here, and we want to update it recursively, so just call it cell, and also for here. Yeah, and another thing is that in this encoder, so when we are using this packed sequence function here, it actually returns a tuple of two entities. The first one is the output, and there's another one which is identical as our source length, being the list of the lengths of the items in our each batch. So I will just put a variable here to unpack this, but we will not use it. Actually, you can just put an underline here, but anyway. And in the decoder, this is wrong. This is actually fc out. And don't forget to run it after correcting. So instead of writing the code line by line for the training function, I actually have already written it, and I will just go through it with you. And I will emphasize on some key points. So here we are using a stochastic gradient descent for the optimizers, although you can use other higher end optimizers such as Adam, but I decided to stick with SGD. And this is our negative log likelihood loss here. We are putting the ignore index of 0 since we want to ignore our paddings. And this reduction, it has two choices. You can set it to min or sum. So when it is in the min mode, it calculates the loss for each batch on non-zero elements that are not ignored, and sum them up, then divide by the number of non-zero items. And if it's in the sum mode, the difference is that it only sums the losses of the non-zero items in one batch, but do not divide by anything. Here we divide it by the batch size instead of the number of non-zero items in the min mode, because we want to treat each word equally. And this is how we actually find out the number of batches we want to train before we enter in the training loop. And if you remember in the beginning, I mentioned that we want to shuffle the batches. This is how we do it. Instead of shuffling the batches directly, we create indices for the batches and we shuffle the indices. So these are the indices of the batches we're gonna use. So if you look at here, the difference between these two numbers will be exactly one batch. And the same as for the target language. In this way, we have shuffled the batches and we don't have any risk of repeating any item for multiple times within one epoch. And also we make sure all our samples are trained in one epoch. So I have this sorting batch here because the padded sequence function will be expecting us to put in a batch that have been sorted by length in a descending order. So I have this function to sort it by length. And here is our validation function. And it will save the checkpoint whenever the validation loss makes a new load record. So our validation functions are essentially very similar to our training functions, but just have some aspects deleted. So here we don't have the teacher forcing because don't need them. This sets the models into evaluation mode because we do have dropouts. And yeah, we're doing basically the same routine as in the training, but now we do not shuffle the batches because we don't need to. And for the test function called translate, it's basically running all in one sample with a batch size of 1, and it takes the sentence and does the tokenizing and the transformation into integer tensor within this function. And here it loops through the process of predicting each word, and whenever it sees the end of sentence token, it will quit. And finally, it will return the list of the predicted words as well as the attention for us to do some future analysis. And here we can initialize our models. And I will show that it actually works with a stack of 2, but in our deployed versions, I'm only using 1 because I discovered that this not making any difference to our accuracy. And I can try to train it to prove that it does train. Yeah, so you can see the loss is decreasing. And after this, I will connect the GPU and train some better models with the whole dataset. And later, I will just be able to load the checkpoints for some evaluations. And before we proceeding into the evaluation for the GRU versions of our encoder and decoder, due to curiosity and as I suggested, I did try to modify our models into LSTM versions, and I tried them once, then later decided to stick with GRUs. So this is our GRU encoder, and this one with some minor difference. Here is the LSTM RNN layer here. So the differences are that because LSTMs have one more state, which is the cell state, and we do need to also unpack the cell state here and return it to be used later in the LSTM decoder. Also, since the cell state will have the same shape as our hidden state, and our encoder is bidirectional, we need another linear layer to shrink our cell state to half of its original shape. And I'm doing it in the simple way here. I just reshaped it and let the linear layer to figure out the parameters itself. So as for our LSTM decoder, it will take the cell state in the fault function that actually exists, and for the RNN layer part, it's also unpacking this cell state. So basically, we are not doing anything fancy with the cell state here. It's not involved in the attention computations. We are just passing it turn by turn until it reaches the final word. So I will show you how it works. So here we have our LSTM versions. They have exactly the same arguments. And let's try training it. So I'm just showing you once for the LSTM version here, and for all our remaining tasks, we are gonna stick with the GRU version. So let's delete those. And here I actually have a already trained version in the checkpoint, and we will just load it and do some tests. And the learning curve, as you might wonder, and I have saved it after my training, and I will just open it up to show you here. So this learning curve actually looks good without any noise, and the training loss reached a really low value at just over 0.1, but the validation loss, as you can see, it is significantly higher, indicating that we are somewhat overfitting our model. My guess is that our model might be still too large, and I might should have tried something like some even smaller hidden dimensions and embedding dimensions. It might help, but I just don't want to tune my hyperparameters further and waste more of my collab computing units, because I do have some even more exciting tasks going on that might show up in my future videos. And actually, the overfitting is very reasonable. If you look at our training data, don't get shocked by the size of nearly 100,000. If you think it that way, our vocabulary size is more than 10,000. Actually, each word in our vocabulary, on average, just showed up for less than 10 times. And that's the average number. So the majority of our words might have only appeared for several times, which really isn't enough to let our model build a reliable embedding. And we're just gonna see how the model performs given all our infrastructures. So first of all, before going into seeing the translation results, I first want to show you how the attention looks like. So let's try with this sentence, because it's a very good representation of the function of the attention. So Tom handed Mary a cup of coffee, and I'm no expert of French, but even if you don't know French, you can see this Mary is here, and it's a different order than the English sentence. But now, if we show you the attention here, we have two attentions because the encoder has two directions. So the Mary in the English sentence is corresponding to the Mary here. And this attention is really working to find the relationship between the essential words in the two languages. And coffee is corresponding to this word, right? So for this another attention, this might represent some other relationships, and then let's try something else. So I just don't want to lose you. Yeah. So this word in French corresponds to the just in English, and this one corresponds to this word, and this is our another attention. So as you can see, our model now really knows which word to look at in the source sentence when translating every word in the target sentence. And I have plenty of such examples which demonstrates the power of the attention mechanism. Then let's actually evaluate our model by comparing the translation results with the ground truth. So we are actually using the samples in the test set that have never been used in the training step, and there's no data leakage. So let's see. Yeah, so these translations actually look not bad. This one has some misunderstanding here, but for the other ones, I'd say they are almost perfect. Yeah, and for this one, the model is not recognizing the word dozen. I think it's because this word appeared too few times in our training set. So few that the model have not built the proper embedding for this word yet. And Yeah, this is really not bad. And sometimes it's missing some words, but it's still making some sense. And we can try more examples. And yeah, the reason why this sentence is not making a lot of sense is also that there are too many real words in this target, and these words are just not trained enough. Yeah, so for the majority of times, the translation is actually satisfiable. Given that our model is actually very small here. So this RNN input thing, if you can recall our decoder, it actually shrinks the size of the tensor from the last step, and so did this W size. It was actually shrinking from 256 to 100, and we have only one stack. So if we have a larger model and a larger data set, it has the potential to perform much better. And our blue score on this on our selected test set, I have ranked to see it's about 53. This looks really high, but our test set was selected. It contains only the sentences with length less than 10, and all the words that have appeared in the test set are ensured to have appeared at least once in the training set. But anyway, I think this is a really good result for our model. So that's all. Thanks for watching, and I will post my code and the datasets onto my GitHub, and you can find them in the link below the video.